Wait, I gotta re-sign in. Okay. Okay. So it's translating a graph.
From graph to function?
No, translating.
Okay, transforming, in other words, the transformations of a graph?
Yeah.
Okay, go ahead, give me the function.
The function is y equals the absolute value of x minus 5 plus 4. Thank you.
What's the parent function?
Y equals the absolute value of x.
How does that graph?
Starting from 0, it's like a big V.
Now, what two things do we have going on that are transformations?
The minus 5 on the x and the plus 4 outside the absolute value.
Okay, what's the 5 mean? Or what's the minus 5 mean?
It means you move it 5 places to the right.
Okay, so the new vertex is there. And then what's the plus 4 mean?
You move it up 4.
Didn't change the slope. Both of those slopes are 1. And that point is 5 comma 4.
5 comma 4. Okay, yeah, I know how to do that.
Yeah.
Um,
As long as you know the parent function, most of those are relatively straightforward. Some can be a little complicated. For example, what is this one? And maybe you haven't had this, but have you had the e to the x function?
e to the x? I think I have, but that might have been last year in trig.
Okay. What are you taking, college algebra?
Yeah.
Yeah, you will have it if you haven't had it yet. Now, if I gave you this function, what's happening? What's the consequences of that negative sign?
You flip it upside down.
Say over the y-axis or over the x-axis?
Over the x-axis?
No, it would be over the y-axis. In other words, the e to the minus x would be that.
Okay.
Here's the thing. That's a horizontal flip. Okay? All horizontal transformations are inside the function. Vertical transformations are always outside the function. So if I gave you this one, then it's a flip over the x-axis, which I would say is a vertical flip.
Okay.
So an easy way to remember these transformations, there's 6 of them, but just remember that anything that's inside the function is horizontal, anything that's outside the function is vertical. For example, what would that be?
A vertical flip.
Inside the function, it's got to be horizontal.
Okay.
What is that?
So it's not a flip, you're moving it to the right.
I took away the minus signs and put up a new function.
Right. So you're moving it to the right.
Correct. So if that's e to the x, then the only point I know is that one there, and that's going to go 2 to the right. So
Okay.
I'm at 2 comma 1.
All right.
But notice why that's inside the function.
Right. Inside the affecting x.
It really means f of x minus 2, which really is what I mean by inside the function. Inside the parentheses means inside the function.
Okay.
If I have f of x plus 2, that's outside the function. That's a vertical shift.
Okay.
If I have 2 f of x, that's outside the function. That is a vertical stretch. But if I have f of 2x, that's inside the function. That's a horizontal shrink. Yeah.
Shrink.
Yeah. So all 6 of your transformations, think of them, separate them into 2 groups, your horizontal ones and your vertical ones. And it applies to reflections. As long as you think of a reflection over the x-axis as a vertical reflection and a reflection over the y-axis as a horizontal reflection.
Okay.
Okay?
I emailed you the next question because it's hard to say.
So how'd you email this? You took a screenshot of your computer?
Yeah.
How do you take a screenshot with control print screen, right?
Well, I have an Apple.
Oh, okay. You have a different, okay. I was just curious on the details as to how you did it, because I'm not sure I know how to do it. I know how to take a screenshot and save it in Paint, I guess, and then I could just save that file and attach it. So I guess I know how to do it.
You can do it with, you can skip that step. If you take a screenshot, it's already on your computer.
Uh-huh.
If you look at what number the screenshot is, you could just type it in on, when you go to the email and you go to add attachments,
Uh-huh.
you can type in the number of the screenshot, like screenshot, whatever, and then it'll come up and you just click enter and it'll load it.
Okay. Good information to know. Thank you. All right. So here they're giving us the sum function. They don't tell us what it is. We could figure out what it is, but we don't need to know. And they say draw the graph of negative g of x plus 3. Well, again, let's take these one at a time. Which one do we need to take first?
A, I guess.
Reflections.
Oh, I thought you were talking about which number.
I mean, the order of your transformations do not matter except reflections have to be done first. And they don't matter in which order if you have 2 reflections. So, in other words, we need to take care of that negative sign before the plus 3. Okay?
Okay, so you flip it.
Which way?
You flip it vertically.
Correct, because that negative sign is outside the function, which is
So
a flip over which axis?
What?
Which is a flip over which axis?
The x-axis.
Okay. So there's the first part. That's minus g of x. And what's the plus 3?
So you flip it over there to negative 4.
Hold on. We're still on the first one. What's the consequence? Oh,
Yeah.
oh, okay, I get you. I heard you say negative 4, and I was thinking he's on the next problem. But
No, yeah.
now I get it.
So then the plus 3, you move it up 3. You move the whole function up 3.
Correct. So it goes, instead of there, it goes right there.
Negative 1.
Doesn't change the shape. Now, notice what would have happened had we done this in the wrong order. If we would have moved it up 3 first, we'd have been to there, right? The black line. You with me?
Yeah.
I didn't draw it right, though. I took it up to 8. I meant to take it to 7. Okay. If we'd have done the vertical move first, we'd have been there. And now, if we flip that over the x-axis, it ends up way down there.
Okay.
As opposed to the correct place that the graph ends up, which is right there.
Right.
So this is an excellent example of why you've got to do your reflections first. Otherwise, you end up with the wrong graph.
Okay.
Okay?
Where does it go up to? Does it?
What do you mean?
Are
Are you talking about if I do it incorrectly?
No, if you do it the right way.
Okay, so we end up here. Let me erase
The two endpoints that aren't at -1, 4. I mean -1, 3.
Okay. Well, first
Oh,
of
no.
all, here, let's get back to theirs. They don't show that as going to negative infinity or positive infinity. They show this as a function that's domain is 0 to 4 only.
Okay.
So when you say where does it go up to, it goes up to however long that is. Okay, in other words, my final function that I came up with, the length of that side is the same as the length of that side.
Okay.
So it goes up to this point right there.
Alright. So wait, I gotta fix.
Now, let's do the second one. Whoops. Must be another page I gotta scroll down here. Can't scroll. The graph of h of x is shown. Are they referring to this?
Are they referring to what? No, it's further down. Give me 1 sec.
Okay.
I can't figure out what cause like, is it the endpoints? Oh, I got it now. Sorry. Okay. All right, let me take a screenshot of this and I'll send it
In
to
other
you.
words, it matters whether there's arrows. If you stick an arrow on those endpoints, it means they go to infinity.
Right.
But if you don't, if you're just drawing a line segment, so whatever the original line segment length was, that's what you end up with. Now, where the exact endpoints are, I don't think you need to know that unless your teacher said label all 4 or all 3 points. And we could figure it out. The endpoint was just a reflection shifted up. So it wouldn't be hard to figure out the exact endpoint.
Right.
Okay, you sent me another one, I think. Okay, this is part B here. Yeah, okay. Oh, what's the function? Can you give it to me? I didn't get it as part of the...
Y equals
It's
2.
It's h. I think it's h of x, right?
Well, yeah, it's h of x.
What is it?
It's 2h times x plus 4.
Not like that.
No, there's no multiplication symbol, but...
Oh, okay. I don't know why I put one in there. Okay. So, what two things are happening? Well, hold on a second. Let me think about this one for a minute. 2h times x plus 4, and they want us to graph it?
They want us to graph it.
Okay. What two things does this thing have in common?
It has a reflection.
So that 2.
That's a stretch, a
Vertical stretch.
vertical stretch.
Because it's outside the function. What's the consequence of the plus 4?
It moves to the left 4 units.
Horizontally. Shift. Left by 4. In other words, you have to spell it all out. So that's what I'm going to do. I'm going to take that point right there, and I'm going to vertically stretch it, and I'm going to move it left to this point right here. Now notice, when I vertically stretch it, it doesn't go anywhere because it's already at 0.
Right.
Okay. But the rest of the curve does. In other words, here I'm going to draw in red without the vertical stretch. Notice that shifts do not change the shape of the curve at all.
Right.
These lines are supposed to be parallel. The red line is supposed to be parallel to that, and that's supposed to be parallel to that.
Okay.
So now when I multiply it by 2, the best way to think about this is if I had a point right there, it would have to be twice as far away from the x-axis, correct? It's being multiplied by 2.
Okay, so
a point that would have been right there on the curve is now down there. So effectively, what a vertical stretch does is it makes that line steeper. See why?
So really, you're just multiplying the
y value.
The y value by 2.
Exactly, and that's what that does. That's what that says. H of x says 2 times the function. Okay,
so
now on this red line, it's also going to be steeper because every point on my green line has to be twice as far away from the x-axis. I didn't draw it quite right. In other words, got to go down to there because that point's at -2, this point's got to be at -4.
So if that point's at -4, the second point's at -4, so wouldn't that go down to -8?
No, remember the red curve is h of x. Red is h of x plus 4 is my red curve. That's all it is. I took the black curve, I moved it left 4 units to get the red curve.
Okay, but then when you multiply it by 2...
Now when I multiply it by 2 and make a vertical stretch factor, it turns into the green curve.
But why doesn't it go down to -8 on the left side?
Well, okay, I haven't drawn it. I didn't draw it to scale. It should go down to -6. In other words, on the left side, that point should be right there.
But the y is -4.
I think it's -3.
Look at the black. Look at the black. That's our original.
Oh, yes. You're absolutely right. You're absolutely right. Yeah.
Okay.
When I did this, I didn't draw it perfectly to scale.
That's okay.
My intent was to show you that we had a horizontal translation that does not change the shape of the curve. And then going from red to green, we do change the shape of the curve. And the way to figure out that it's always a skinnying, in other words, you're increasing these slopes, is to think about a point that would have been on the red curve is now going to be twice as far away from the x-axis on the green curve.
Okay.
That's the way to think about them. And that way you'll always remember what does it mean if I do, what does it mean if I do y equal 2x squared? Well, I know that y equal x squared is a parabola. What's the consequences of the two? Outside the function.
Oh yeah, it's outside the function, so it's a what's it called? A vertical stretch.
Stretch. And what does that have on this parabola? Does it flatten it or make it skinnier?
It makes it skinnier.
Yeah, and you can see why. In other words, if you should ever forget, which it does,
It makes it steeper.
well, that's because that point right there is twice as far away from the x-axis as the original point would have been.
Right. So why, when it's inside and you're working with x, why does multiplying it by 2 stretch it?
Doesn't it? Shrinks it.
What?
Here.
But
let me pull up another one here. Let me pull up my, let me just pull up my page. If you're familiar with the sine curve, that's inside the function. Here's what a normal sine curve looks like. This is inside the function, but it acts as a horizontal squeeze, so that my new sine of 2x is going to look like this.
okay.
So what I'm really saying is that these have opposite effects. If I have an A there and a B there, if A is greater than 1, acts as a stretch. If B is greater than 1, it acts as a shrink, opposite.
Just because of how multiplying the x by 2 is different than multiplying the y by 2?
Yep.
Okay.
When A is between 0 and 1, it acts as a shrink factor. When B is between 0 and 1, it acts as a horizontal stretch. So it's
right.
opposite both ways. So
if you have like a B times, so if your B was 1/2 x, so you would have, that would stretch it. It would be double the length. Right.
Correct.
Okay.
Okay. And there's no difference between the sinusoid function and what we're doing now on polynomials. Notice that everything in the sinusoid function, I'm assuming you've had this.
Yeah, it's been a while, but.
Yeah. They don't call them the same thing. They call that amplitude, and they call that's associated with period, and they call that phase shift, and they call that vertical shift, but they're all the same. In other words, that is a vertical stretch factor. That is a horizontal stretch or shrink factor. That is a horizontal shift, and that is a vertical shift. And if I stick a negative sign, that's a vertical flip. And if I stick a negative sign in front of the x, that's a horizontal flip.
Okay.
The reason I used the sine function is because it best illustrates the difference between all 6 things you can do. Every single one of them results in a different curve.
All right.
If you're trying to illustrate transformations by this function, doesn't really work because y equals minus x squared, which would be a horizontal reflection because the negative sign is inside the function, well, that equals x squared. So it doesn't show any different. In other words, if I draw my original parabola and try to show the effect of this minus sign inside the function, I reflect it over the y-axis and it looks exactly the same.
Okay.
So this is not the best function to show transformations. Actually,
right.
The reason I introduced you to e to the x, or not introduced you, but introduced it to our conversation, was because this also has 6 different graphs based on the 6 different transformations. But even e to the x is not quite as good as the sine wave. The sine wave really illustrates the difference between each transformation. All right,
Gotcha.
let's go back to your...
I sent you another email, which is a different problem. This one, it definitely isn't as complicated, and I think I know how to do it, but just want to go over the reasoning for it.
Yeah, I can take a screenshot by doing that. And I wonder if I could actually attach that to an email. I bet I could. I haven't figured out how to do it yet. The reason I do it is because it allows me to draw on it, which is really a valuable tool. I didn't used to have this capability. You'll probably remember, I never could do this a year ago.
Yeah, I remember.
But I ended up discovering this capability, and it's been wonderful for tutoring. Because I don't have to redraw all these. I can just go straight to it. Fortunately, I don't have the instructions at the top. What do they want here?
Oh, so they want to know, for each graph, select all symmetries that apply.
Okay. Kind of simple.
So when something is symmetric across the y-axis, it has to be in the top right, in the 0 to 90 degree place.
The best thing to do is look at one of these and tell me if it's symmetric about the y-axis. Are any of them?
Well, yeah.
Which one?
About the y-axis, just B.
Right. Because that is the reflection of that. That's what makes it symmetric. Got to be a perfect reflection. Well, notice that my first curve, if I wanted a perfect symmetric, it would have to go like that. And it doesn't. So that does not have symmetry with the y-axis. Also doesn't have symmetry with the x-axis. But it does have symmetry with the origin.
What does? The A? Why? If it's diagonal, it has symmetry with the origin?
Symmetry with the origin is when you flip it over the y and the x-axis. So if I were to flip this curve over the y-axis, it would look like that. And then if I flip it over the x-axis, it's exactly where it is. That's why that's what symmetry with the origin is.
So B is y, x, and origin.
Well, yeah, hold on. Let's first of all finish A.
Okay.
A is only origin.
Right.
B is definitely x because that's the same as that. It's definitely y. And I guess if it's x and y, it's also symmetric with the origin because, in other words, if I take this part right there and I flip it over that, I get that. And then if I flip it over the x, I get that. So yes, it has all three.
Okay.
How about C?
C is symmetric over the x-axis.
Okay.
And over origin, I think.
Not origin. There's nothing on the other side. So
okay, so just the x-axis.
Yeah. In other words, if you have a point in the first quadrant, if it's symmetrical with the origin, that point's going to be over here.
Okay.
Because you'd have to flip it over the y-axis and then again over the x-axis.
Right. So yeah.
You can't have symmetry if you don't have any points in the other curve. Now what if that curve on the right looked like this? What if it was shifted up 1 unit.
It wouldn't be symmetrical over any of the axes.
Correct. Would not have symmetry. In other words, everything has to be relative to the origin or the x and y axis. This might have symmetry over the line y equal 1. The way I drew it kind of does. It's got, excuse me, it has, yeah, this is kind of a key point here. It would have symmetry with the line y equal 1. Now, when we say symmetry with the x-axis, that means the same as symmetry with the line y equals 0. The x-axis is y equals 0. That is the line that makes the x-axis. Just like y-axis is x equals 0. And that can be a little confusing if you're not used to it. We know horizontal lines are y equals. We know vertical lines are x equals.
Okay.
Takes care of this one?
Yeah. So now it's another symmetry problem, but I could vocalize it.
Okay. Bring up.
So it's telling me for each equation, determine whether the graph is symmetric with respect to the x, y axis, x-axis, y-axis, or the point of origin.
Okay.
And the equation is 8x to the fourth plus 28y to the fourth equals 30. That's the first one. I know there's some way by looking at the leading coefficient and the roots that you can determine it, but I don't know what it is.
They want to know if this is symmetrical with the all three, huh?
Oh yeah, which ones of the three?
Well, let me think for a minute. I think we need to talk about odd and even functions. You familiar with them?
Yeah.
An even function means f of minus x equals f of x. And even functions have symmetry with the y-axis.
How can f of minus x equal f of x?
Well, take the cosine curve. If I go in this direction, looks like that.
Oh.
So here's x, there's f of x. And here over here is negative x, get the same f of x.
Does that have to do with the leading coefficient being even or odd?
No, well, I don't know about that yet. First of all, I want to talk about even and odd functions because that may be how we have to solve this. I'm not sure yet.
Okay.
But this is true. In other words, if a function is an even function, like y equal x squared is an even function, that's the best one to remember because the exponent is an even number. That has symmetry about the y-axis.
Okay.
And it's also true that, I guess it's better to use f of x notation in these. It's also true that f of negative x is equal to f of x.
Okay.
If I plug in negative x and square it, it stays positive x. So f of negative x is equal to f of x on all even functions.
So so that means x to the fourth is an even function.
Correct.
Mm-hmm. So it's definitely
symmetry about the y-axis.
So yeah, that definitely has symmetry about the y-axis because it's
about odd functions. There's only five, even and odd.
Do even have symmetry from the point of origin?
No, I don't know yet. I think think of a function as both even and odd, it might have, but an odd function, f of minus x is equal to minus f of x.
Okay.
And odd functions have symmetry about the origin. Notice the sine function. We know that has symmetry about the origin. We can see it, right?
Right.
Well, it's also true that if the sine of minus x is equal to minus the sine of x. So if a function is odd, then it has symmetry about the origin.
So if it was x to the third.
Maybe. Now, let's talk about that for a second. In the previous problem, we saw that that circle had, whoops, I don't want to erase that. That circle had all three symmetries. Has symmetry about the y-axis, has symmetry about the x-axis, and has symmetry about the origin. Well, the equation of a circle is x squared plus y squared equals r squared. Okay. So, if I plug in a negative x for x, get the same equation. So it's got symmetry about the y-axis. If
Well, isn't the function that we're looking at the top, isn't that a circle then?
no, that's an ellipse, I think.
Oh.
And it's not a circle because the coefficients are not the same. And what the symmetry it has is probably not, in other words, here, let me draw an ellipse. Because an ellipse is a lot like our circle. It's liable to have all three symmetries. This is an ellipse at the origin. And the reason I know that is because there's no x term, there's no y term. Here's the equation of an ellipse, first of all. It's x squared over a squared. Have you had conic sections?
I'm sorry, what'd you say?
Have you had conic sections? Ellipse?
No.
Seems a strange problem that they would give you. I'm not sure I've completely worked it out. But this is the equation of an ellipse. And we can see that the ellipse has symmetry over the y-axis. It has symmetry over the x-axis, which means it has symmetry over the origin.
What's the difference between an ellipse and a circle?
Circle's equation is x squared plus y squared equals r squared, where the coefficients are the same in front of the x and the y.
Okay.
Notice that if the coefficients are different, then they're going to end up as a different a and a b over here. So it's going to be an ellipse. Whether it's a horizontal or a vertical ellipse doesn't much matter. I don't think it affects the symmetry. In other words, it might be an ellipse that looks like that. Either way, it's got all three symmetries. Now the question is how we know that. First of all, that's not an ellipse. It's x to the fourth and y to the fourth. Not even sure what that looks like. Let me pull it up on Wolfram Alpha and we'll have a look at it and then we can tell. And that's a way you could always tell, I think, is by plugging it into your calculator. Let me plug it in.
If you have x to the fourth and y to the fourth, though, can't you use u substitution?
You can, but that doesn't quite make it an ellipse, and I'll show you why. First of all, I'll put it in as an ellipse. What is the equation again? It's
8x to the fourth
I'm going to make it
plus
squared. Go ahead.
28y to the fourth or second
Equals,
equals 30.
see, and the nice thing about Wolfram alpha tells you exactly what you put in. So I now know that I put it in perfectly. And that's an ellipse. We can tell that has all three symmetries. Now let's make it y to the fourth and see if it changes it. I bet it's going to change the shape a little bit. It might still have all three symmetries, and I suspect it probably does. But it's not going to look exactly like that ellipse. Notice it's more of a square with round,
What a weird...
round corners. However, still has all three symmetries.
Right.
And that's the key. Now,
Okay.
I guess that they wanted you to graph it and figure out the symmetries from looking at the graph. Because it's a strange question otherwise. In other words, I'm not sure how we do it. It would appear that it has all three symmetries, but the odd symmetry is what's curious. In other words, f of minus x is not minus f of x. So it doesn't appear to have odd symmetry, but maybe we got to solve for y and get it in terms of y equals something. And then maybe it would have odd and even symmetry according to these mathematical definitions. In other words, any problem that you can answer by looking at the graph, you should be able to answer mathematically also.
Right.
In other words, if I can look at this graph on Wolfram alpha and see all three symmetries, then I should be able to come up with a way of making sure that it's an even function and it's also an odd function. Part of the problem here is it's not a function. And when I say part of the problem, it's not a function. It doesn't pass the vertical line test. Okay?
Right. Oh,
so
okay.
If I have a function, then I can apply that even and odd. For example, a very nice odd function to remember is y equals x cubed. Okay, or let me say f of x equals x cubed. Now, I can test this. What does f of minus x equal? That's always the test to determine whether it's even or odd.
Minus f of x.
That's true. It's equal to minus x cubed. When I plug in minus x, that cubes to this. So we know that symmetry with the origin. And if you graph it, it graphs kind of like this. Sure enough, that's symmetry with the origin. And that's a good one to use for odd because that exponent is odd. So my two favorite functions for illustrating odd and even are y equal x squared and y equal x cubed. Because that tells you whether they're odd or even based on the exponent. And then you can kind of go from there. But notice this does not have symmetry with the x-axis. And the reason it does not is because it wouldn't be a function if it did. If I had something on this end of it that looked like that, well, it's immediately going to flunk the vertical line test. So when you're dealing with things that aren't functions, which are called relations, there must be a different criterion for determining odd and even. That's all I can say. And I'm not sure I've ever learned what it is. Probably has to do with y. In other words,
Okay.
and our function, but even that doesn't look odd. No, I'm not exactly sure how you use the odd and even property to figure out that a circle has all three symmetries.
All right. Well, it's one question. Y equals 8x. Maybe that one's simpler.
It will be.
It's odd, for sure.
Oh, just y equal 8x?
Yeah.
Okay, well, first of all, let's put it in this notation and prove that it's odd. How do I prove it's odd?
F equals F times minus x.
F of minus x. That's not times. Important distinction.
It equals minus 8x.
Which is equal to minus f of x, which makes it odd.
Right.
Okay? And that one we don't need to graph to see it. In other words, if I were to graph it, it's a straight line with, and the fact that it's odd should have symmetry with the origin, and it does.
So odd always has symmetry with origin?
I don't think there's any such function that has symmetry with both axes and the origin. Wouldn't be a function. And that's why that ellipse or elliptical looking thing was not a function. Now, or it had symmetry with all three. And
Right.
no functions can do that because it would violate the function if it had symmetry with the x-axis. That automatically violates, it's not a function if it has symmetry with the x-axis.
Okay. So if something's odd, it immediately has symmetry with what? The
Origin.
the origin. And if it's even, it has symmetry with the y-axis?
Correct. And the easiest way to remember that is remember these two functions. Which one is odd? Which one's even? Getting a note, degraded audio. Can you still hear me okay, Max? Max, can you hear me?
Hey, yeah.
Okay.
Yeah, I don't know what happened.
My GoToMeeting said I had degraded audio for a moment. But of these two functions over here on the far left, which one's even and which one's odd? Still there, Max? I'm going to call. Yeah, let's finish the audio out on our phones. If that's all right with you? Okay. Because I'm having audio quality problems. Now it says it lost the connection. Can you still see my screen?
I can. It hasn't told me that I lost connection yet.
Okay. Over here on the far left, do you see a y equal x squared and a y equal x cubed?
No.
Okay. Imagine it. Which one is even? Which one is odd?
Y equals x squared is even.
Correct. And you know how to graph that. So if you graph a parabola, you know that it's got symmetry over the y-axis. And so this is one way to always remember what's even and what's odd. Because you know how x squared looks, you know the symmetry, and you also know how x cubed looks. And you can figure out that that's got symmetry over the origin, and it's also an odd exponent. Now, did you get reconnected? Looks like you might have. What number am I writing on my screen?
No, I didn't get reconnected.
You didn't get reconnected, did you?
Let me see if I can.
Well, here's one thing to try. Disconnect from GoToMeeting and re-enter using the same meeting ID number. Try that while we're on the phone. I'll erase that 7. Now I want to leave, I'm going to write a different number, and I want you to tell me when you can see it. GoToMeeting's been having a lot of problems lately, although this could be on my end. We have so much snow that it might, I actually, I had 4 power outages in 10 minutes yesterday during a session. You were lucky you didn't get that, but the guy after you got it, and we weren't able to finish the session. Our power kept going in and out.
Try writing something, because I think I did.
I've written a number on there.
Yeah, I can't see it.
Okay, did you try disconnecting from GoToMeeting? Close out GoToMeeting.
Yeah.
Because it never showed on my end that you got disconnected. Interesting. So you disconnected, closed out, and came back in. And on my end, it just shows you as having been there the whole time. I'm going to, here, let's do it this way. I'm going to disconnect, GoToMeeting.